So today what we do, we are approaching the topic of the decomposition, the model approach for continuums. I think that several of you already know for the n degree of freedom. So what I do, I make a quick I summarize the fundamental steps that are driving the model approach into the n degree of freedom, in order to make a parallelism. So the scope of the today lesson is to make a parallelism among what is done in the n degree of freedom, what we do into the continuum that is extremely similar, very, very similar, and what is different, of course, and the limitation. But there is the possibility really to have an intuitive view of what is done into the continuum, just in a very close similitude of what we do into the n degree. So we start with n degree. I make the very usual drawing. All right, so we assume that we have a system, n degree of freedom. There is, we are taking care of the elastic problem, assuming that it is a fully linear small displacement. And so at the moment, we don't take note of the any damping. And so we are speaking about the elastic problem. So for analyzing the kinematic and studying the dynamic and using typically the Lagrangian approach, we are writing the n equation of motion of the n degree of freedom system. We will have a mass matrix, a stiffness matrix, the vector of the free coordinates. Those are the free coordinates, free independent coordinates. Lagrangian coordinate, it means that they are independent, they are free. They are free, it means that we can make any change in each of them without affecting the other. And we can assume that all of them are null instead of one. So, the assumption that they are free coordinates is the fundamental assumption. And then we can study the force motion, the free motion. We study the free motion. Studying the free motion, we study eigenvalues and eigenvectors, natural frequencies and eigenvectors. All right. With the eigenvectors, we are building a transformation matrix that is the matrix with the eigenvector for each positioned by columns like that. This transformation matrix that we call phi, if I'm not wrong, into our representation, yes, is what is defining the transformation. So we are saying that the transformation in principal coordinate is writing x equal and so it is interesting that we are defining the principal coordinates through the transformation matrix phi. So this object here is the transformation matrix, but we are not writing q equals something. We are writing x vector, the vector of the free coordinate, equal phi multiplying the principal coordinate. This is defining the principal coordinates. This is allowing us to write the problem in a very simple way. So I make a substitution like that. So I write the second order derivative of x will be the constant matrix multiplied second order derivative of q. And so I write m phi q dots plus k phi q equal f. And so I just substituted instead of x this quantity, instead of x2 dots this quantity. The point is that if I pre-multiply now everything by phi transposed, what is happening is that this object here is a square matrix I keep writing the vector of the forces with the parentheses, but is not really relevant. And what is happening is that it's possible to demonstrate that m star is diagonal, k star is diagonal. It means that m a j star is equal so making this product of phi transposed times the mathematics times phi given that this mathematics was derived, is symmetrical as it was derived by the Lagrangian operator applied to the dynamic of the system. So there are some constraint that we have to give. So the fundamental constraint is that M and K, they must be symmetrical, and they must be derived using the energetic Lagrangian approach over the system. So this is much better. But given those small constraints, what is happening is that the product phi transpose M phi makes a diagonal matrix. Phi transpose K phi makes a diagonal matrix. That is that M star ij is, we call it Mi star. It means modal mass of the ith mode when I is equal to j. So in the location 1, 1, 2, 2, 3, 3, whatever, we have an object that we call Mi star. It means the modal mass of the ith mode, Ki star. It means that in the location, we don't call it Kii. We call the mass matrix of the modal mass of the first mode. And so we call it M1 star. The mass the stiffness mass, the equivalent stiffness, the modal stiffness of mode 3. We call it K star 3. All right? Because it is obvious, because it is possible to demonstrate that whatever I different than j makes Kij equal to 0 when I is different than j, Mij equal to 0 when I is different than j. All right? It is possible to demonstrate all of that. Let's have a look. Let's have a look anyway of what we do when we are making this product phi transpose M phi. This is it is useful to have the practical feeling of what is happening. So what is happening is that when we are making phi transposed, this is phi transposed multiplying the M, multiplying phi. When we are building the n by n matrix M star at the location Mij, we are writing the number that is given by the ith row of the phi transpose, that is the ith eigenvector. So phi is the matrix of the eigenvector. Phi transpose is the same matrix, but they are positioned by row. And when we are making the product of 3 square matrices, one square matrix in the middle, one square matrix here, and that is the transpose on that, the element Ij here is the ith row of this matrix multiplying what is in the middle, multiplied by the jth column here. And so the Mij is right. So the orthogonality property of the transformation in principal coordinate is that the eigenvector, the ith eigenvector, is orthogonal to the jth eigenvector through the mass matrix and through the stiffness matrix. So if that is m I star different 0, 0, I different 0. Okay? If we are speaking about the same eigenvector, this cross product makes a number that is different than 0. If we're speaking about the two different eigenvectors, it is null, because the eigenvectors have the property of being orthogonal through the mass distribution, through the stiffness distribution. So this is the orthogonality property that we studied into the n degree of freedom system. And what we are doing, and we will understand, and we will demonstrate that what is happening working with the in the continuum is exactly the same property, but written a little bit in a different way. Now, in order to understand what we do into the continuum, let's start with the example. All right, so our problem is this one. We have a continuum, for example, a beam that is simply supported at the extremities. We have a time-space distribution of excitation, and we want to calculate the time-space distribution of displacement. All right. We already know a piece of that. We already know that in an ideal object like that, but that is fundamental in order to understand something that is totally generalized for the more complex condition. We are writing the partial differential equation that is telling the equilibrium of the infinitesimal element. We are fixing the boundary conditions. That is what we are working with into the exercises in the present. Then we will put over that the excitation the distribution of external excitation space and time dependent. But first we do that. First we do the study of the free motion. And studying the free motion, we understood that attaching the boundary condition to the partial differential equation, we write the free motion as the superposition of what we wrote as the functions that are the eigenfunctions of the problem that are multiplying a time-dependent harmonic function that is running at a frequency that is very specific of the mode omega 0I. So we learned that we are studying the problem with boundary, the free motion problem with boundary condition. We are finding out the natural frequency that are making null the determinant of the matrix of the coefficients of the homogeneous problem. And together with those associated to each of those natural frequencies, we are defining a function of space that is the modal shape of the specific mode associated to that object and to those boundary conditions. And we have a very, very clear idea that this function here is an harmonic function that is running at the specific frequency of the mode. All right? This is clear for us now. Now what we have to do. So first of all, the role of the transformation matrix that we are working with in the n degree of freedom is now taken by, and we use the can I cancel this, the orthogonality property? All right, we know that this is the orthogonality property. In order not to make confusion, I'm canceling. So we know that in the n degree of freedom, the reason for doing this transformation of coordinate is to make advantage of the orthogonality property. Now we keep in mind that the transformation matrix that is the fundamental tool into the n degree of freedom is becoming the vector of the eigenfunctions. And we are saying that in the notation of the slides, phi, the function was written as phi I x in this notation. For some reason, when I wrote those things, I used a different notation. I don't know for which. Is coincident with phi I x. So the functions phi, function of space of the continuum, are the eigenfunctions, are the modal shapes, are those objects here that I am drawing here. Those are the function phi. So this is phi 3 function of x. All right? And we are starting to keeping in mind that they are the equivalent in the continuum of the modal shapes described as eigenvector into the n degree of freedom. And we will use it as a vector of functions made like that. All right? Next. Yes, yes. So, but let's say that we should have the practical vision that here we have a mode shape when the three masses are moving all together to the right, for example, and this could be the first mode of vibration. Maybe that the motion is a little bit different here and there, but we can have a third mode of vibration that is where the vector x1 could be 0.8, 1, 0.9, all right? But the second mode could be that here we have 1, 0, minus 0.7. And so the second mode could be that this goes plus, this is almost in the middle, not moving much, and the other one moving back. And so the second mode could be that when this is moving this way, that one is moving that way, and the one in the middle is not moving much, right? And so the shape of the mode of vibration can be shown here. So if positive, so of course the displacement goes in this direction, but I could say that I could make a drawing that what is plus is over. What is negative is below. And so I could say that the first mode is represented by something like that. Something like that. So this is the first mode. That is equivalent to say that is very similar. So in our imagination, we have to figure out that there is a shape into here. The second mode could be that this one is almost null, very, very small. This one is positive. One of those could be 1 because we are normalizing. The model shapes must be normalized. It's also possible not to normalize, but it is much more useful. Almost always we make so that the model shapes are normalized to 1. The maximum is 1. The other one are less. For which reason? Because it's useful, all right? It is useful. It is very useful to normalize the model shape in this way. Because when I am reading the amount of movement through the principal coordinate q, when this is 1, it means that the largest is moving 1. I could normalize to 1 million, but it could be, I will have numbers here that are 0.00001, all right? And so it is not, it is meaningless. So the normalization is something that is in order to make meaningful the number with which we are playing. And typically the normalization is made to, so it is made so that the largest number of the object, the eigenvector, is equal to 1. All right, so is it clear? Is it clear now that what I have into the eigenvector is the shape of the mode of vibration? Is in an n degree of freedom? Yes, but I recognize absolutely a shape. I recognize the shape in which they are moving. When I am working with the continuum, the shape is much more clear, is absolutely clear. So I look at this shape, the other shape, and it is extremely clear, all right? But the concept is absolutely the same. One is in a granular way, so the discrete number of location, and the other one is distributed into the continuum. All right. Well, so the point is that what we write is so instead of writing the transformation in principal coordinate through the definition of the principal coordinate given by the transformation matrix, because take in mind that this transformation is defining the principal coordinates. When I was studying like you, I was saying, but for which reason we don't write q equal to something in order to define the q, all right? It is a good question. Why? Why don't I write q equal to something that is telling us how much is the value of q when the value of the natural free coordinates is a set of coordinates, a set of numbers. So I really think that you could be much more interested in knowing that into this transformation is written that when the shape is 0.8, 1, 0.9, it is happening that this is the first mode. And so the Q1 is made equal to 1, and the Q2 and 3 are almost equal to 0, all right? And we write reversed. But we write reversed because what is relevant is not to know how much is the value of the principal coordinate when I am giving some values of the intrinsic natural coordinates. What is very relevant is the property that is associated to those principal coordinates given a transformation that is written in this way that it makes very, very easy to find out the properties. So the fundamental reason is that writing the transformation of coordinates in this way, it becomes straightforward to show that it holds the orthogonality property, and so we are writing directly a diagonal problem like that using the principal coordinates and just having to estimate the diagonal numbers M1, 2, 3, 4, K1, 2, 3, 4. So it becomes natural that we have to work in this way. We have to define what is X given the principal coordinate. This is the way in which it becomes clear the fundamental property of the transformation. And so the definition of the transformation of coordinate X equal to something is made now saying that we can represent whatever movement of the continuum through a linear combination of the modal shapes, multiply each of them by a function of time. What we have to understand what is the meaning of what we are writing here. And there is a great risk. The first great risk is that the function gi function of t looks like being exactly those functions here. So some of you could say, but you are just saying, naming in a different way what you are writing here. Instead, not. We are saying something totally different. Here, so we have to understand what is the meaning of what we are writing here. Here, the function gi, function of time, are perfectly known, are the harmonic functions running at the frequency omega 01 for this one, running at the frequency omega 02 for the second, running at the frequency omega 03. So the function gi, t are known quantities. The magnitude is not known. I would say that I will express that the free motion is given by the superposition of the GIT scaling, multiplying, modulating the modal shapes with specific amplitudes. But they have a very fixed time-dependent shape. So they are harmonic functions. The harmonic function of the frequency 1, 2, 3, 4, that's it, it's finished. All right. And they allow us to represent just the free motion. It is totally not possible to use those quantities in order to write the forced motion. The free motion is disappearing. The free motion is disappearing. The free motion is disappearing because the system is always damped a little bit, and so you have the free motion. The free motion is disappearing. You have an excitation. The excitation is arbitrary, and so the movement of the system. We pretend to say that the movement of the system is represented by a superposition of the modal shapes, each of them modulated by a time domain function that is, and here is the point, the unknown of the problem. So the unknown of the problem, that is the object of the study of the dynamics, is the function, Qi function of time, that are that multiplied by the modal shapes are giving the representation of the way in which is moving the system is moving as an effect of the excitation. What should we say about that? First of all, is that for which reason we should accept this? So the real point is it possible that whatever is the configuration that could be reached by this structure, this totally arbitrary configuration that could be reached could be represented in such a way. But in order to do that, I suggest you to make this effort to stop the time and to think that the formed configuration that is reached by the system in a certain time is like a picture. You take a snapshot, you take a picture, you fix the time, and you take the picture that the structure has. And you pretend that this shape that about which you make the drawing, can be reached, whatever is the possibility in the infinity way, in the infinity space of configuration of the structure, can be represented by a combination of the modal shape, each of them multiplied by a real number. So what I say is that if I fix the plot of the structure at a certain time, what I am doing, I am simply multiplying the modal shape times each of them by one number, a real number. A real number for modal shape 1, a real number for modal shape 2, a real number for... And the point is that I am saying that if I am using all the modes, and here is infinity. Here is infinity. So the real point is that here is infinity. So I pretend to represent whatever possible configuration reachable in the space of configuration of this problem with the superposition of the modes. Yes, but I have to use all of them, and they are infinite. All right? In order to understand that it's not so far away that it's possible to do that, I think that we can be very much more comfortable saying that, understanding that those modal shapes have a shape that is somehow following the fundamental constraints, the boundary condition. So those shapes are coming from the partial differential equation that is saying the dynamics of the system must obey to the dynamics of the infinitesimal element. But then we are asking that on top of that, we are limiting and we are fixing that the boundary condition must be satisfied. And having satisfied the boundary condition, we find out the natural frequencies, we define the modal shapes, and so all those modal shapes, all of them satisfying the boundary condition. So for sure, superposing all of that, I am always making a drawing that is perfectly satisfying the boundary condition. All right? That is the fundamental point. Next, the real point is that the property of the modal shape is that they are a set of functions that have the property that they are a complete in the mathematical language. They are a complete. They have the property of the completeness. They are a complete base of functions into the space of configuration reachable by the structure. You understand what I mean? So it means that there is the property of the completeness. So so it is, nothing is out of that. They are complete. Of course, if I am using 1/2 of that, the 1/2 of that is not complete. I cannot pretend to represent the full, the full space of configuration if I'm not using the full set of functions. All right. Well, so I hope that we got the problem. Next, the point is that the function qi, function of time, they have absolutely nothing to do with gi. So now I try to convince you that they have absolutely nothing to do with the gi, because the point is that the idea that there is a link among gi and qi is a very strong idea, and is very difficult to get rid of that. So I show you a problem. I show you a problem where it is obvious that so let's try to figure out, in case I have a cable here, tensional cable, I apply here a force, and this force has a frequency that is a generic frequency different from whatever natural frequency of the cable. Okay, we are not matching any natural frequency of the cable. We are keeping far away from any natural frequency of the cable. What will happen to the behavior of the cable when it will vibrate, having passed the free motion? So after having what to say? Having stopped the free motion, so after a certain time that we will have a free motion, initial free motion, but the free motion, we say, we are forgetting, we are discarding. We are discarding because it is done. But instead, the forcing excitation here is continuous. And so what is left after the consumption of the free motion is the response to the excitation. What are we expecting that is doing this system that is excited by the frequency omega? Is vibrating at the frequency omega. So a linear system, whatever linear system excited at one frequency is answering at that frequency, having finished the free motion. All right? This is a totally general. Cannot do anything else than vibrating at that frequency. All right? And so when I pretend to write that the actual response of this structure to this excitation is written through the superposition of all the modes, and you see that now I stopped here. I stopped at n. I will never use all of them infinity. It's not possible, it's not feasible, it's not useful. I realistically will stop always, and I will select. But let's say that I take the first n, all right? And so I will write the response of the system in this way, and we are learning that it's possible to do it. And what I want to show up that having demonstrated that it's possible to do that, then which will be those quantities that are shown here? They must be written as so they will be exactly the same. So the Q1, Q2, Qn unknown that are defining the way in which the system is moving, they will be exactly the same function, the harmonic function running at the same frequency of the excitation, but multiplied by a constant that is different for each of them. A complex constant that is saying which is the amplitude and the phase with which the mode 1 is answering to that excitation, the magnitude and phase with which the mode 2 is answering to that excitation, the magnitude and phase with which the mode 3 and so on are answering to that. So the meaning of what we are doing, we are saying that we are representing the way in which, in an overall way, the system is answering to the excitation as the superposition of the way in which each single mode is answering to that excitation. And then all of that is superimposed. But in my opinion, it is useful to look at an example like that where, in my opinion, should be intuitive that given an excitation at that frequency, the system is answering at that frequency. And so pretending to write the general motion in this way and being those quantities the unknown of the problem, finally, in this case, is totally clear that they are all the same, equal to the harmonic function at that frequency, but weighted, but different constants. And it will be finished. And so it's becoming very, very simple. All right, so I hope with this example to have somehow convinced you that GI has nothing to do with QI. Those are known, and those are the unknown of the problem. All right? Well, so we go ahead. But this is the key point, otherwise we can be confused. Then next, I would like to convince you that the structure of what we are doing, saying so the tools with which we are playing are n degree of freedom, the vector of n free coordinates, the matrix of transformation, that is the matrix of the n eigenvector, the vector of the principal coordinate. Into the field of continuous vibration, we speak about the vector of the eigenfunctions, that is totally equivalent to the matrix of the transformation to the matrix phi. Here you have the eigenvector, that is the model shape 1, the eigenvector 2, that is the model shape 2, the eigenvector n, and here we have the eigenfunction 1, the eigenfunction 2, the eigenfunction n, all right? So this is the eigenfunction 1, eigenfunction 2, eigenfunction more, all right? So we are playing with the vector of the model shapes or the vector of the eigenfunctions, the vector of the principal coordinate. And what we are writing is that the transformation of coordinate is this one, is written here. The motion of the system in time and space is written equal to phi transposed, this vector here, phi transposed times q. That is exactly the same as saying matrix phi of the n multiplying q. Consider that if you are looking to this transposed here, means that we are working in the way that we could have done differently, but we are working with a vector of coordinates. The shape, you could imagine that is here, x is moving here, and so the eigenvector is made by row instead of being made by column. And so you have the first row, the second row, the nth row. And so in order to make the product, I have to say phi transposed in order to match with the first one, the first, with the second, the second. And so we are writing that the transformation in principal coordinate is writing the free motion of the system equal to the first eigenfunction, that is describing the shape with x that is moving from 0 to L here. And I would write that you are reading that here there is the equivalent of the eigenvector that is into the n degree of freedom, but just represented very simply as phi function of x, finished. But of course, we have the drawing here that is exactly this one. And then the second eigenvector, that is the second eigenfunction, the nth eigenvector, that is the nth eigenfunction, and finally there is the vector of the principal coordinate that is exactly the same. So we know everything, so we go home and we finish, all right? More or less. It is equal. It is absolutely equal. It is totally equal, all right? but it's written in a little way, in a little differently, all right? Well, so this is the transformation in principal coordinate. Of course, you notice that I have to stop. I have to stop at n. All right? I have to stop at n. And this is the great advantage. So this is the one of the fundamental advantages of working with the principal coordinate. So if the structure about which we are playing, with which we are playing, is excited by a force distribution, this is Fx time, all right? If the structure is excited by a force distribution that is spanning over the axis of frequency, of course, this is a time domain function, all right? But if we make the Fourier transform of this time domain function, we have the spectrum. I must speak about the spectrum of the excitation because you know what is a spectrum, all right? You did measures. You did the 3 courses of measures, almost more or less, 2 at least. Just 1, no 1, nothing, I don't know. But you did mathematics. And you know that the function of time can be totally perfectly written in terms of the equivalent transformation in, with the Fourier transform. We have the exact replica of the time domain into the domain of the complex coordinate S, all right? So we are, if you are looking into the domain of the Fourier transform, so if we are playing with the spectrum of the time domain excitation, we could recognize maybe that the spectrum of this excitation is limited in bandwidth, or could be limited in bandwidth, but with a maximum and with a minimum, all right? And so if I have modes staying here, and as we know that what will end up will be that the modes of vibration of the structure will answer to the excitation very strongly in case the excitation is matching the natural frequency of the mode. This story is always the same story, and I hope that you have the feeling that if you are exciting a structure, matching the mode of vibration with a very small force, you can excite with a large amplitude without any effort, all right? This feeling must be in your sensitivity, okay? I suggest you to play with a system that can move in order to feel yourself with your hands that you can excite the system in resonance, and you can play with very, very small forces to have a very large amplitudes, all right? You must have this feeling, doing yourself. All right, so we know that the system is answering strongly in case the spectrum of the excitation is meeting the frequency of the modes. And so the modes that are here, it is useless to be modeled if the excitation is there, all right? I can do it, yes, but they will not participate. What is fundamental here in order, if the spectrum of the excitation is this one, is that the natural, the modes that having a natural frequency that is into the bandwidth of the excitation are modeled, all right? And so if I have to answer to the question, how many modes I have to take, and do I have to take the first, all the low frequency modes because it is important? Could be also not. Could be that in a situation like that, if I want to represent the dynamic of the system, and the bandwidth of the excitation is here, and in the low frequency there is almost nothing, it is interesting, maybe, to limit the number of modes with which we are playing, and to consider just those, eliminating, forgetting the first 1, 2, 3, whatever, and then forgetting the one that are over the maximum frequency of the spectrum of the excitation, all right? And so the suggestion, how many modes we are taking, and is it allowed to stop, and are we making a large mistake limiting the number of modes with which we are playing, have an answer into the problem in which we are facing, all right? Of course, if I have to represent with this model representation of the structure, not just the response to the excitation, but also the free motion, it is important that into the free motion, all the fundamental modes are shown. And so if I pretend if I have something in which I want to give an answer, putting together the free motion, in which way it is evolving the free motion together with the effect of the excitation, if I have a system that is starting from an initial condition, and I'm starting together with it, with this also the excitation, and I want to represent everything, I have for sure to take care also of all the low frequency modes, because generally the low frequency modes are strongly represented into the initial condition response of the system, all right? And so the answer, how many modes I am taking and which one we can neglect, is let's say, is a task of the designer. It's a task of one who has some understanding, and so he has to decide himself, not because the teacher is saying you use this, and that. No, you have to decide. You have to decide because you have to understand which are relevant, which are not relevant. So, all right? All right, so I hope with this general view to have given you the flavor of what we are playing with, and the flavor that what we are doing with this transformation here is exactly the same that we do in the n degree of freedom with the phi multiplied q. All right? Well. Next. So the statement is this one. So first, we are representing the time-space distribution of the movement of the structure through this position. The eigenfunctions are known, the principal coordinates are unknown. This is the new unknown of the problem. And so the unknown will be a set of n functions, right? All right, so all of that is limited to a number of n functions, all right? Our problem will be always limited to a finite number of n functions. Those n functions are the unknown of the problem, all right? But phi, the vector of phi, is known as the modal shapes. What we are doing, we pretend to write the energetic quantities of the problem, that is the kinetic energy, the potential energy, and the work of the external forces when we are writing the first motion of the problem, through this representation in principal coordinate. Let's make an example, so to be very practical. So I start from the end of the problem in order to make it very clear. Let's try to follow me. What is the meaning of what we are writing? We are going to write there. I have the beam or the tensioned cable. Let's make the example of the tensioned cable that is easier, but the example of the beam is exactly the same. So we write something that is more similar to a tensioned cable. All right, so this is the tensioned cable. I have an element of this length dx, all right? I want to write the kinetic energy in order then to write the Lagrangian approach. We must know the Lagrangian approach for dynamics. So we must know that we will write something that is so we will write the Lagrange operator written for a system of independent coordinates, Q, having defined that the kinetic energy, for example, will be functions of those Q unknown through the representation of the distribution of kinetic energy, that is the distribution of the velocity of an element having length dx, mass m, function of x. So I have a cable having a mass that is dependent on the coordinate. It has a tension. At this point, the tension is not relevant for the kinetic energy. Whatever is the way in which is moving, the kinetic energy will be represented as the total kinetic energy will be represented as the integral from 0 to L of what? Of this object here, that is unit, the mass of the element dx multiplied by the square of the velocity. Of course, we will write, the task will be to write the square of the velocity through this. So what we are doing is to make the exercise of putting this position into here and making the integral. All right? In order to go to right to the end with something that is understood, I do not follow everything here. I do not. So now I should write together with the kinetic energy also the potential energy. All right. The potential energy should be written for the cable that is written in some way, in a certain way, for the beam that is written in another way. All right. But let's stay on the kinetic energy. All right. We stay on the kinetic energy and we look at in which way all of that can end up. So this is the way in which we are writing the kinetic energy of the cable. All right? So in order to make it clear, practical, let's open what we are doing. So in this representation, we have the transpose vector of the eigenfunction. That is function phi1, a vector, so a set of quantities. The function phi1, the function phi2, the function phi(n), multiplying the vector. So we make rows by columns. And so what we are writing phi1 q1 dot plus phi2 q2 dot plus phi(n). So we are making this addition of all those elements, and then we are asking to all of that to make it square. All right? So it looks like to be very, very complicated, all right? But we do not do the square. We say that this object that is phi1 times this. So it is the addition of several quantities, but this object is simply what we call a scalar. All right? What is a scalar? If A, B, C are quantities, numerical quantities, A plus 3B plus 85C is a scalar, all right? And this is something very similar, all right? This is a function multiplying another function, but it is a scalar function, all right? It is the addition of quantities, numerical quantities that are, finally is a scalar, is a combination of functions. Some of them are unknown, some other are known, but is simply the addition of functions, all right? And so eta is a scalar, written as the product of two vectors, one that is phi transposed, the other one that is q not transposed. What we say is that eta is coincident with transpose. So this transposed of a scalar is still the same scalar. So the transposed of 1a plus so eta transposed is coincident with eta, all right? Here the two vector is, the first vector is 1, so 1, 4, 58. The second vector is A, B, C, all right? So this is the vector 1, 1, 4, 58, and the other one is A, B, C, all right? We can keep it separated, the two vectors. But we write that the eta, the transpose of a scalar is the same scalar, all right? And using this evidence, we are writing that, can I cancel this? Can I cancel this? Yes. So let's keep in mind that I wrote eta. We have to keep in mind eta equal okay. My position is eta is phi transposed times q, all right? Eta transposed is q transposed times phi, all right? What I write is that eta square is coincident with eta transposed times eta. It's the same. Eta transposed is coincident with eta. And so eta square can be written as eta transpose times eta. For which reason is useful? Because instead of writing this object here, that is very complicated, totally useless to be, we cannot handle, totally impossible to handle, we write eta transposed times eta. but eta transpose is q dot t vector transposed multiplying phi vector. So this is eta transposed. Eta transposed is q dot transposed multiplying phi. So eta, did I write it? I have to write somewhere that eta is equal phi transpose time q. All right? So eta is phi transposed time q. Eta transposed is q transposed time phi. Eta square is q transposed times phi transposed time q dot dx. So the kinetic energy is written as this quantity. Now we switch the position of something. Which is this something? Is where can I do it? I do it here. So the kinetic energy is integral 0L 1/2 mass distribution square of y dot. Y is written as phi transposed time q, transformation principal coordinate. Partial derivative of y dot, or partial derivative of y with respect of time, is phi transposed time q dot. So that kinetic energy is m, function of x, phi transposed q dot square dx. We use the trick of using eta and eta transposed. We call this object eta, and we write eta transposed time eta. And so finally, this appears as First of all, 1/2 outside. The quantities that are not depending on time, they go outside of the integral, all right? What we wrote, we came here, we wrote eta transposed time eta, that is q dot phi. Phi is function of x, phi transposed is function of x. This object is function of x. This object is function of x, q dot goes outside, and the other q dot goes outside because they're function of time. And what is left is into here. Let's try to understand which is the shape of this object here. This object has the shape of the function phi. I'm making the product of the vector column times the vector row. It makes a square matrix. It makes a square matrix where in the ij location, we have phi I, function of x, phi j, function of x. So this is the product. The vector phi, so you make the first times the second, it is 1, 1 here. Then the first times the second, the first times the first, 1, 1. 1 times the second, 1, 2. 1 times ith, 1 I. 1 times the n, the 1n element. Next, 2. All right? So it is necessary that you have the feeling that a column times a row makes a square matrix. If you don't have it, you must get it. Okay, all right? Well, so we understand that writing things in this way, we understand that what we are doing, we are making a nice matrix where I can position here m function of x. M function of x is multiplying all of that. So m function of x is multiplying the matrix. And I have to do the integral of the matrix. That is the integral of each element of the matrix. That's it. All right? If we say that we do the integral of everything, we are taking out of the integral the vector of the function of time. But we can also say that the integral of the matrix is the matrix of the integrals of the element of the matrix. It is exactly the same. And so what we are writing is that at the ij, in the ij location, we have integral 0L, distribution of mass, eigenfunction phi I, eigenfunction phi j, multiplied dx. And this is finished. And so, and what we are finding? We are finding that at the location phi I, at the location ij of the product phi transposed m phi in the n degree of freedom, okay? Look back to the very first. In the location ij of phi transposed m phi, I said I have the eigenvector xi multiplying this mass matrix, multiplying the eigenvector xj. Okay? So in the n degree of freedom, what we are writing is that the m star ij is eigenvector I mass matrix eigenvector j. And the orthogonality is that this product is null if I is different than j. What we are doing in the n degree of freedom, we are weighting the distribution of mass through the eigenvector I and the eigenvector j, calculating m star I, j, and discovering that they are all null unless on the diagonal. Here, what we are doing, we are recognizing that we can write, now I cancel this, we are recognizing that with the transformation in principal coordinate, making this small trick of saying that eta transposed is equal to eta, and now we are speaking just about of the kinetic energy, but for the other quantities, potential energy is absolutely exactly the same. What we are finding out is that we can write the kinetic energy. Let me see in the way in which I write here in the notes. What I write is something like that. Phi, the vector phi is clear what is the vector of the eigenfunction. The vector q is the vector of the principal coordinates that are the unknown of the problem. Now here I do not write the vector q1 dot q2, but I write the q transposed, knowing that q is the vector column, so q transposed is the same but positioned as a row. And into here I have, in the location 1, I have integral 0L m function of x, phi1 function of x, phi1 function of x, dx. At the location ij, I will have m star m function of x, phi I function of x, phi j function of x, dx. Integral 0L at the location nn, m function of x, phi n function of x, phi n integral 0L, all right? So, the architecture of the kinetic energy with this position is a quantity that is a square matrix of objects that we call the modal mass matrix. So these objects are the modal mass matrix. But we are showing that for the elastic problem, the orthogonality property is that using the transformation in principal coordinate, that is this one, that is writing the movement of the system as the vector of the modal shapes transposed, multiplying the vector of the new introduced principal coordinates. So using those newly defined coordinates as the new unknown of the problem, using this transformation, it's possible to write the kinetic energy in this way. the representation of the kinetic energy is in using a set of n modes that must always be limited. We can go to infinity. It is a numerable infinity. We can stay all our life to calculate all the numbers. It is useless, all right? We are stopping sometimes. It is possible to demonstrate that from a theoretical point of view is holding the perfect equal, it is absolutely equal if we consider all the infinity terms, but it is a mathematical approach. In the practical approach, we are saying that we are stopping because the mistake with respect of the exact solution is totally negligible. And this square matrix is telling the story of the weighting of the mass distribution through the shape of the ith mode and together with the shape of the jth mode. And we recognize the orthogonality property is that we can demonstrate that the I, j elements are always null in case I is different than j. So the orthogonality is that the modal shapes weighted by the mass distribution are given a cross product integral equal to 0. And so we recognize that, of course, in case we have that the modal shape of the very simple beam or cable, tensioned cable, for the tensioned cable, we are pulling here, and the first mode is this one, the second mode is that one. If the mass is constant, of course it is orthogonal because the harmonic functions are orthogonals. But in case the modal mass is not, in case the mass distribution is not constant, the two shapes themselves, the integral of phi I times phi j integrated over dx is not null. The integral phi I times phi j is null, so the shapes are geometrically orthogonal in case the mass is constant. In case the mass is not constant, they are not orthogonal. What is orthogonal is not the shape. What is orthogonal is the shape weighted by the mass distribution, but it was exactly the same also in the n degree of freedom because we have the transformation matrix phi transposed, another transformation matrix phi, in the middle there is the mass matrix. We cannot forget the mass matrix. When we are making the transformation in principal coordinate in the n degree of freedom, we have the eigenvectors outside, but in the middle there is the mass matrix. In the middle there is the stiffness matrix, all right? So we pretend in this course that you have the concept that what is orthogonal is not the geometry. Of course, then the example, we do the example on a constant mass per unit length, and so what is orthogonal is the geometry. And it is very, very clear that this shape is orthogonal to the other one, all right? But we must have the concept that in the general case, it is not a geometrical property. It is a property that is involving the mass distribution, that is involving the stiffness distribution. And so, and generally speaking, what we write is that the key property that we are recognizing that we should demonstrate is that M is that integral 0L M function of x phi I x phi j x is equal, and here we write mi star different 0 I equal j 0 I different j. All right? This is the orthogonality property. The orthogonality property is that this quantity is, and this is what we call the modal mass. So when the last time we were speaking about the omega 0 square equal square root of something over the fraction line, something else below the fraction line, and we introduced the concept of modal stiffness, modal mass. Now we have the analytical expression of the modal mass. Now we can fix the constant that is multiplying the total mass of the cable or the total mass of the beam. Here we had M times L, and then we said, but maybe we have a constant here or another constant here, and the ratio of the two is stiffness divided mass and giving the frequency. Yes, we understood that what is over the fraction line is something that is the modal stiffness. Below the fraction line, there is something that is the modal mass. But doing the dynamics of the structure, we can calculate. So we calculate actually exactly what is the modal mass, is the weighted distribution of mass integrated through the model shapes. All right? And the orthogonality is that all of that is diagonal. Well, in my opinion, we did the fundamental concepts. The application of all of that on the stiffness is exactly the same. It's the repetition of exactly, but there is the expression of potential energy for the cable, potential energy for the beam. I ask you to work on the writing of the potential energy for the beam. We do together the potential energy for the cable. That is a little bit, there is a concept. The potential energy of the beam is something that belongs to the previous thing that you did, but we can repeat it. I hope that the fundamental concepts are clear. Is it? I hope. All right. Sorry I was a bit late, but I had the conference before.